Sunflowers are a rich source of vegetable oil with a wide range of uses from cooking to feedstocks for biodiesel. Vegetable oils contain a mixture of triglycerides. These consist of 3 fatty acids linked together by a glycerol molecule. In vegetable oils like sunflower oil, the hydrocarbon chains in the fatty acids are polyunsaturated, which means that they contain several carbon-carbon double bonds. This causes the melting point of the vegetable oils to be relatively low, so they are liquid at room temperature. They also have a low viscosity, which means they will pour easily. In the food industry, vegetable oils are used in the production of margarine. In this process, liquid vegetable oil is converted into a solid but spreadable product. This is done by adding hydrogen atoms to some of the carbon-carbon double bonds, a process known as hydrogenation. This process happens on an industrial scale, as the EU produces over 2 million tons of hydrogenated vegetable oil each year. The double bond in unsaturated molecules consists of a pi bond and a sigma bond. This can clearly be seen in the structure of ethene, the simplest alkene. The pi bond, which has an electron density above and below the plane of the carbon-carbon bond, is critical to the mechanism of hydrogenation. Hydrogenation requires a catalyst so that it can happen in a controlled and economical way. Hydrogen molecules can adhere to the surface of several metals, including nickel, in a process known as chemisorption. Rather than simply colliding elastically with the surface, chemical bonds are formed between the hydrogen molecule and the metal surface, eventually leading to the dissociation of the hydrogen molecule into hydrogen atoms. The pi bond of an alkene molecule also allows it to chemisorb onto the nickel surface. This causes the pi bond to break open, leaving a single carbon-carbon bond. Each carbon atom is then bonded to the nickel. In the next step, the adjacent absorbed hydrogen atoms react with these carbon atoms to form a saturated molecule. Finally, this saturated hydrocarbon is released from the surface, a process known as desorption, and diffuses away. In this reaction, unsaturated vegetable oil is mixed with powdered nickel to form a slurry. This is then introduced into the reactor. Hydrogen is pumped into the bottom of the reactor, and as it bubbles up through the vessel, it comes into contact with a mixture of catalyst and vegetable oil. The hydrogen is bubbled through at 5 bar pressure. This increases the rate at which the hydrogen collides with the surface of the nickel. The reactor is maintained at a temperature of 150 degrees centigrade, which not only increases the frequency of collisions with the nickel surface, but also ensures that a high proportion of the molecules will collide with the surface with sufficient energy to chemisorb and react. Any unreacted hydrogen is captured as it emerges from the reactor and recycled back into the reaction mixture. The hydrogenated product is also separated from the nickel. The nickel needs to be in a fine powdered form, as this increases the surface area and allows more molecules to chemisorb and react every second. The product molecules may still contain some double bonds, but are much more saturated than the starting material. However, the mechanism of the reaction converts these double bonds from a cis into a trans-geometrical arrangement, as seen in the structure of allylic acid. Recently, health concerns have been raised about the presence of trans fats in processed foods, including margarine. The altered shape of the more saturated hydrocarbon chains allows them to pack together more closely and increases the melting point. The margarine produced from these hydrogenated fats is now solid at room temperature, although its melting temperature is carefully engineered to ensure that it spreads easily on hot toast.